All right, we're still in 4.4. I can't seem to get out of this section. But this is among the last topics that we have to study in here. This is about the second fundamental theorem of calculus. So you might see that abbreviated SFT, maybe SFTC. Remember, the fundamental theorem of calculus is officially called the first fundamental theorem, but it's so fundamental that we typically just call it fundamental theorem of calculus. So enough about the wordplay. Basically, as it says here, the second fundamental theorem of calculus shows us how differentiation and integration are related. So what we're being asked to do here is to solve a problem like this, where you differentiate this integral. Okay, and I want you to kind of notice that this integral is a little bit different from maybe what we've seen in the past, and that it does have like an upper limit that is a variable x. Okay, we dabbled with a little bit of this, maybe in a different free response or note sheet or something, but that is kind of the big difference here, because it's not like that is a 5 or a 10 or another number up there, which is what we're used to. So let's try to figure out if we can figure out the answer to this by doing step 1 down here, where it says let's do the integral first, and then step 2, then let's take the derivative, right? Kind of working this problem from the inside out. So in step 1, we're going to look at this, and we're going to actually integrate it. And of course, to integrate this, we have to use the first fundamental theorem of calculus, which says that we're going to find the antiderivative of t squared, which is t cubed over 3, and then we're going to evaluate it from 3 to x. All right, once I do that, I get x cubed over 3 minus 3 cubed over 3, and I feel compelled to write that as x cubed over 3 minus 9. Okay, so that's what's inside the parentheses. We've got x cubed over 3 minus 9, but then remember that there's this operator on the outside here where it says to take the derivative of that integral. So if the integral is worth x cubed minus over 3 minus 9, I'm now going to differentiate that and see what I come up with. So let's get back into derivative mode in our brains, where we're going to apply the power rule. So we're going to bring the 3 down front and decrease it to a power of 2, right? When we do that, there's already a 3 in the denominator, so that kind of cancels. And the derivative of minus 9 is 0 because it's a constant. So I guess the derivative of that equals x squared. And so now I want you to take a nice long look here at the original question and think about what has happened. If the derivative of that integral is x squared, how are differentiation and integration related? So much like addition and subtraction are inverses of one another, and multiplication and division are inverses of one another, we also have integration and differentiation being inverses of one another. Because the function that we started with here, t squared, right, if I integrate it and then differentiate it, my outcome is just x squared. So all it does is it kind of goes through, I don't know, this is dumb. In my head, it just kind of changes costumes. So instead of being written in terms of t, it is now written in terms of x. So instead of it being the integrand t squared, it's x squared. So basically, the differentiating undoes the integrating. So if we look down here, the official way that we would write the second fundamental theorem of calculus is that anytime we're asked to differentiate an integral from any constant to an upper limit that is the variable x, that is really important because that did play a role in transitioning the integrand from t squared to x squared. The integrand is usually written in terms of t's, and what we find out, right, is that we do this little costume change, and that instead of it being f of t, we now switch this over to f of x. It's the same function, just in terms of x. So that's the connection between these two ideas. So let's apply this here for a couple examples down below. We'll talk about a corollary, and then maybe we'll look at some AP-style questions that are multiple choice that might be on the an exam. So example 1, same format. We've got the derivative of this integral. Good news here is that the lower limit is a constant, such as pi, so that counts as a C value. Upper limit is a variable. That's cool. So since I'm being asked to differentiate this integral, I can just change the variable of the integrand over to x instead of t, and I'm done, right? So the object here is not to actually integrate and then differentiate, right? We actually do not want you to perform the operations. We just want you to pick up on what the pattern is for when you see these operations next to each other. So example 2, right? Go ahead, type that in the prompt. And if you correctly put x cubed plus 2x plus 1, you did it right. Example 3 takes us on a little switcheroo here. So all this does is it flips the limits. So now we've got the constant on top, and we have the variable on the bottom. So this doesn't make it any harder. We just have to remember, like we normally do when we flip the limits, right? Flipping the limits makes the integrand opposite, or makes the integral's value opposite, and that's exactly what it does here. So if we flip the constant to the top and the variable on the bottom, we would end up, with negative x cubed minus 2x minus 1, right? It's literally just the opposite of what happened in example 2. Okay, and then the last one here is example 4, where I'm providing you with a different notation, but it's the same question. So now we're using function notation here. So we have named this function, that is the integral from 5 to x of the root of t plus 2 dt, as capital F of x, right? That's just the name of the function. So now, if I'm asked to find f prime, right, this problem is actually asking me to differentiate that function. So if you wanted to take a moment to write it out, right, you're being asked to differentiate this integral, right, and that would follow the same patterns as examples 1 and 2, right? We would just change the variable that the integrand is in terms of, and we would switch it over to root x plus 2. So just a little brief note about notation change there. All right, on the second side, we are going to look at a little corollary to the second fundamental theorem. And a corollary means, if you see if you can figure it out, what has changed in examples 5 and 6 and 7 that's different from what we saw on the first page. So kind of scan those, scan these, right? Hopefully you're noticing that this upper limit here is no longer just a variable, it's a function of x. So it's a totally new kind of question. So if we differentiate, okay, the integral from, again, the bottom is still a constant, but now the upper limit is a function of x, right, which we would call f of x. And actually, you know what? Remix that. We actually don't call it f of x for these problems. We call it g of x because the integrand still takes priority and is called f of t, like the previous example. So if we differentiate this integral, right, we could do the same thing as before, where we figure out like what actually happens. Like up here in steps 1 and 2, we actually integrated, we actually differentiated, we figured out the connection, and ooh la la, that was cool, but sometimes it's harder to see for this one. So I don't want to necessarily go through all of that for these problems, so I'd rather just kind of cut the quick and kind of show you what happens here. So what happens is that we take the composite function f of g and we multiply that times g prime, right? So this is composite here, plug the upper limit into the integrand, and then multiply by the derivative of the upper limit. And now you can see why it was really important to call one f and one g, so we could distinguish between the two. So let's apply this. Oh, probably to make it easier in our lives, let me make this green so that when we do this, everything matches. Okay, so let's look at example 5. Again, here is the f of t function here, sine of t. And then g of x is the upper limit, right? So it's really important to kind of remember which is which. And then we're going to plug x squared into sine of t. So that's now composite, right? Sine of x squared. And then we're going to multiply that by the derivative in green of g prime, which is 2x. So this is my answer. You can try example 6 on your own. And if you did that right, same idea. We want to plug x cubed into the integrand. So it's 4 over x cubed. And then we want to multiply by the derivative of x cubed. So this time we're going to multiply by 3x squared. Now, if this question pops up in a multiple choice, right, we are going to have to be able to simplify this to 12 over x. Cool, right? Right. So speaking of multiple choice, let's look at example 7 here. It is, I don't know, pulled from an exam, just a random multiple choice question. Here is the question part of the problem, and then your choices are below. So let's think about, which theorem this is. Is it the corollary or is it the original? Should land on the fact that it is the corollary because that upper limit is x cubed. So now we're just going to apply the pink times the green like we did before to get the derivative of this integral. So I'm going to plug x cubed in for t. So my function is going to become ln of 3x squared plus 1. So that's the composite part. And now I'm going to multiply by the derivative of the upper limit, which is 3x squared. Okay. Now if we kind of scan these answer choices here, it looks like we might have to do some simplifying because right away I may be thinking about this one looks similar with the 3x squared there and the ln of x squared plus 1 here, but I notice that's not really right. So let's see if we can figure this out and which one of these makes sense, because this is the hard part of multiple choice questions. Not always like, what's in the pink and green here, that's the answer, but clearly that's not a choice. So now we've got to massage it a little bit, right, till it fits the choices that are there. So let's kind of work with this a little bit. So the ln of, I guess this would be 9x squared plus 1. And then times 3x squared there, which, since that's outside, 3x squared times ln of 9x squared plus 1. I don't see that there. Oh, no wonder why our answer choice isn't there. Let's rewind. Let's not put 3x in here like a moron. Let's go back and put x cubed in there, right? So this is ln of x to the 6 plus 1 times the 3x squared. Okay, exhale. That looks a little bit better, right? And now if you just rewrite the order in which these multiply, that does end up being choice C. Oh, my bad. All right, let's look at example 8. Last one. It says, which of the following is an equation of the line tangent to the graph? So we're trying to find an equation of a tangent line. And then here is the function they are giving us. And then the x value is x equal to -1. So this is a hot mess of a function, a, because it's including the integral notation in it. So our job, if we're going to write the equation of a tangent line, right, is to write y minus whatever the y value is equal to the slope, which is the derivative, and then x, in this case, plus 1, since the x value is -1. So let's get the y value by plugging -1 into this function. So the way that I see it, That's kind of right up here. Y of negative 1 is 3 minus the integral from negative 1 to negative 1 of e to the negative t cubed dt, right? So the input for this function is this x value here. It's not the t. The t is not the variable. The upper limit is the variable. And we know that this whole integrand is going to be worth what? That is worth 0 because those limits match. So y of negative 1 is equal to 3 minus 0, which of course is just 3. So that means this question mark is 3. I'm on the right track because if I scan all the answer choices, they all start with y minus 3. And now I've got to come up with my slope. Fix this equal sign. So now let's do the slope here would be whatever the derivative of the y function is when you plug in negative 1. So let's take the derivative of this. You can kind of probably see where we're going with this. Differentiating one term at a time, the derivative of 3 is 0. I'm subtracting the derivative of this. So is that the original fundamental theorem or is that the corollary? We're applying the original fundamental theorem because the upper limit is just x. It's not a variable. It's not a function of x. Sorry. So the derivative of that is just going to be the integrand e to the negative x cubed instead of e to the negative t cubed. So now if I plug in, negative 1 to that, I get negative e to the negative of negative 1 cubed. So you've got to wade through all these negative signs to figure out this is negative e to the positive first power, right? And that's just negative e. So to me, that looks like negative e belongs in the slope spot, and that would be choice B here.